Alright, hello, we're back. We're gonna see if my live stream this time is working. Seems like the stream health is green. Oh, no, it's not. Okay, lovely. This is great. Maybe I shouldn't watch the stream as I'm streaming. I don't know. But yeah, this internet connection's amazing. Having a lot of fun with it lagging and doing different things that it's sort of not supposed to, pixelating and all that. Alright, well, I guess it's finally stable. So we're going to go over some example problems regarding Newton's first law, force, mass, and Newton's second law. So the first problem, the first three problems are going to be a little bit more conceptual, and the fourth problem regarding Newton's second law is going to be a little bit more algebraic, and you're going to need to maybe pause and then solve it yourself. So Newton's first law. Imagine a spacecraft going at a velocity of 900 meters per second with the engines off, exiting our solar system. Assuming it doesn't crash into anything, would it go at 900 meters per second forever? Well, as we know, Newton's first law is that a body in motion tends to stay at motion and a body at rest tends to stay at rest. So since the engines are off, and assuming it's not crashing into anything, yes, the spacecraft would keep going at 900 meters per second in space. Now, the second question regarding Newton's first law is, imagine a car drifting with the engine turned off on Earth. Why does the car stop? So, there's a couple different things playing into the car stopping. First of all, the engine's off. So if it was in space, yes, it would keep going. However, in space, there's no external force acting on the car. When the car is drifting, there is a downward force exerted on it by Earth, which is the force of gravity, the gravitational force, which is what causes it. Well, there's that, and then also friction. Force of friction is also sort of causing it to stop. So, theoretically, if there was a non-frictional surface that it was going on or moving across on with the engines off, it would keep going forever until the frictional surface stops and moves onto a frictional surface. So it's not necessarily the force of gravity that's stopping it. The force of gravity and the frictional force is causing it to stop because of the force of gravity as well. So here we have the second question. Well, I guess third, but second group. Force. If we have a rubber band attached to a nail on a block, what happens if we pull the rubber band tighter and tighter away from the block? So I have a little bit of a picture representation over here as well. The first picture represents, here's the mass, and here is the rubber band, and here's the nail. So if we pull it this way, but not very tightly, the rubber band isn't really going to do anything. It's just kind of going to be there. However, if we pull it tighter, we may exert enough force, applied force, onto the rubber band, which in turn exerts a force onto the mass, which might move the mass this way, depending on, how heavy it is and how much tension there is. So we are essentially applying the force onto the rubber band, and the rubber band is therefore, it has some tensional force as well. So that's essentially what happens. The rubber band just kind of stretches out. And it may or may not move the mass, depending on how heavy it is. If we go into some conceptual questions about mass, we have we have A and B. So if we have a huge spring attached to a house and we pull the string with a semi-truck until the spring is totally stretched out and the semi-truck stopped, what would happen in each instance where the semi-truck has more mass than the house or where the house has more mass than the semi-truck? So, here's our little visual representation. Here's the semi-truck, a terrible drawing, and then here's a house, a slightly less terrible drawing. And then here is the spring. So we know that the mass here is here, and then there's a mass here. So depending on if M1 is greater than M2, what happens, and then what happens if M2 is greater than M1. So obviously we have the spring, so if M1 is greater, then the house will spring towards M1. M1. But if M2, the house, is greater than M1, the truck, then the truck will spring towards the house once, the engine of the truck turns off and everything comes to a halt. All right. So, here comes our little bit more algebraic problem, Newton's second law. Regarding Newton's second law, a certain force gives object M1 an acceleration of 12 meters per second squared. The same force gives M2 an acceleration of 3.3 meters per second squared. What acceleration would the force give to an object whose mass is the difference between M1 and M2 and the sum of M1 and M2? So, we know that Newton's second law is equal to F equals M times A. Now we have a certain force, and then we also have the same force gives M. So if we were to write an equation for both of these, we would have F equals M sub 1 times 12 meters per second squared. And we also have F equals M2 times 3.3 meters per second squared. 30, sorry. It's important to note that because, yes. All right, so we know that these two are the same exact force, meaning that these two must also be equal, which means that M1 times 12 meters per second squared is equal to M2 times 3.30 meters per second squared. Now, if we solve for one of the m's, say M2, then we have M2 is equal to M1 times 3.64 meters per second squared. Now, where do we go from here? That's the question. So, we can always rearrange F equals MA to anything, such as F over M equals A, or F over A equals M. So let's take this one, because why not? So F over M1 equals 12 meters per second squared. Then we have F over M2 equals 3.30 meters per second squared. Now this is important to note that we did this because since we have 1, 2, 3 unknown variables, we can't exactly have one equation that will solve for them. So we need this here. We'll use that later. And we'll definitely use this. So now going back to A, if we find the acceleration for the same force acting on the difference between m1 and m2, we can rewrite that as F equals m1 minus m2 times a certain acceleration. Sorry, I just have my notes on my whiteboard up there. Just peek at them. Right. So essentially what we're going to do is, since we have here m2 and we have m2 over here, we can plug this right into m2. So we'll do F equals m1 minus m1 times 3.64 meters per second squared times the acceleration. We can solve that F is equal to negative 2.64 meters per, negative 2.64 m1 times A. I'm just thinking, do we need the meters per second squared in there? No, because it's a ratio. Okay, so forget this part here. Yeah, because these were supposed to cancel out. My bad. Alright, at least we figured it out, though. Okay, so now these equations over here are going to be handy because we can rewrite this as F over negative 2.64 m1 equals a1. So what do you notice as a pattern here? We have F over m right here, meaning that you remember that this is 12 meters per second squared is F over m. So if we plug that straight into the equation, 12 meters per second squared divided by negative 2.64 is equal to a1, and conveniently I calculated this out and it's negative 4.55 meters per second squared is the answer for part A of the question. And essentially we're going to do the same thing with part B, except the equation is just a little bit different. So we have F is equal to m1 plus m2 times a2. And we're going to use the same equation equation between the masses that we got up here. And we're going to plug m2 back into m2. So F is equal to m1 plus 3.64 m1 times a2. So when we do that, we get F is equal to 4.64 m1 times A2 F over 4.64 M1 equals A2. And we notice F over M1, we plug it in as 12 meters per second squared divided by 4.64 equals A2. And for that, I think I got 2.56 meters per second squared. And that's our second acceleration. So, the important thing to note here is that we first set up an equation that the word problem gave us. We set up the two equations. We wrote down the first, Newton's second law. We rearranged it a little bit. And then we found some connections in a way. So we found that the same force is applied in both situations. So we could just set the two masses and their accelerations equal to each other because it's the same force equaling the same ratio of mass to acceleration. And then we just solve for one of the masses. So we got a little bit of a ratio there. Then we took part A and we created an equation for part A regarding F equals ma, but we changed it around a little bit because we were looking for the differences between the two masses. And then for that, we plugged the ratio equivalent of M2 into M2 and then solved and found the pattern that F over M1 was already solved for because that's just the acceleration of that specific mass. Plugged that in and then we got the acceleration. And we did essentially the same thing for part B. So yeah, hopefully that was helpful. I'll try and figure out some more things about my internet. My stream times might change. We might be streaming midday when no one's online. So yeah, tune in next time, probably tomorrow around midday. I don't know, I'll probably post something about it. So keep